In the previous lecture of my series on the representation of the permutation group Sn, we had met Frobenius' theorem. And the theorem gave us a formula for determining compound characters for a group G, starting from the simple characters of any one of its subgroups H. The formula goes as follows. The compound character corresponding to the nth class of G, psi L, sigma. Here sigma is just a label which tells you which irreducible representation of the subgroup H this is coming from. This quantity is given by the following. It's a sum over KL tau, that is, it's a sum over all classes of H which are contained in the nth class of G. And what you add up is the ratio G by H of the orders of the two groups. When you multiply this by HL tau by GL, here HL tau is the number of elements in the class KL tau of H, and GL is the number of elements in the nth class of G. And finally you multiply this by phi L sigma, that is the simple character corresponding to the L tauth class, actually. So this is really phi L tau sigma, the simple character corresponding to the L tauth class of H, of course corresponding to the sigmath irrep. This gives us a formula for the compound character which can evaluate for each and every class of G. And a very important special case of this comes about when you take the 1th irrep or the identity irrep for H, in which case all the phi L tau sigmas are 1, and the sum over all classes descended from the nth class of G simply becomes the number of elements of KL which survive into H. And that number is what we call HL. So this particular formula for the special case gives us a compound character value for the nth class given by the simple ratio G over H into HL over GL. In addition to the statement and the proof of Frobenius' theorem, in the last lecture we also discussed applications of this theorem. In particular, what we did was use our knowledge of the irreps of S2 to derive compound characters for S3, and then from those figure out the simple characters of S3 and therefore the S3 character table. This one was reasonably straightforward. We also started from S3's character table and worked out S4's. And the S4 character table turned out to be this one. Let us move our game up a notch and try to figure out the complete character table for S5, the next symmetric group. Now at this stage you might be getting a bit bored thinking that we are repeating the same thing over and over again, but as you will soon see, S5 throws up its own challenges. So it's not going to be exactly the same thing all over again. But let's make a beginning. At this point, up here I have listed all the cycle structures possible for S5. These of course labeled each and every one of the classes. So here you have a situation where you have 5 1 cycles. That of course is the identity and identity alone, a single number in that class written in red out here. Then you have a class with 1 2 cycle, 3 1 cycles, and the number of elements there can be easily figured out from our general formula 120, the order of the group itself, or 5 factorial, divided by 2 divided by factorial of this 3 here for the 3 cycles, and that gives you 10. In a similar manner, you can fill up the entire top row here, all possible cycle structures, and as we had already figured out in the last lecture, there are 7 of them. And using our formula, we can figure out the occupancies or the number of elements in each of these classes. As a check as to whether we have done the thing correctly, you can just add up all these numbers and you should of course get 120, which is the number of elements in S5. Now, we are beginning our job with Well, not really a completely empty slate, because we do know two one-dimensional representations of S5. One of them is a trivial representation where all the elements of the group and hence all the classes get labeled by 1. And in the other, you have the alternating representation where all even permutations are labeled by 1 and all odd permutations are labeled by -1. Let me remind you once again of our rule. A permutation belonging to a particular class will be odd if it consists of an odd number of even cycles. That's the case here, here, and here. On the other hand, this one doesn't have any even cycle at all, or this one has 2 even cycles, so all of these correspond to +1. The odd cycles, the overall odd permutations correspond to -1. So that's my second one-dimensional representation. So when we begin, we already know these two. Now let us try to figure out the compound characters using our formula. And for that, we are going to take the characters from S4 in sequence and try to find out the corresponding compound characters. And as we have done before, try to figure out the simple characters from there. So first, let's try to figure out Chi1, which of course is the compound character which we get when we start with this representation, the identity representation or the trivial representation Phi1 of S4. Of course, these columns were labeled Chi1 a while ago when we were talking of S4 representations. Now we are really thinking of S4 as a subgroup of S5. Now, before we fill in the numbers, let me just point out that there are classes in S5 which definitely has no elements in the corresponding subgroup of S4. Here, we are thinking of S4 as that subgroup that we get when we consider the last element of S5, element number 5, fixed. So element number 5 has to be in a one cycle of its own to begin with, and then we are simply going to forget about that particular element. Whatever is left will give me a permutation of 4 objects, which is an element of S4. So the criterion, of course, is there has to be a single one cycle at least so that our element number 5 can reside there. Now, of all these cycle structures, you can see this one does not have a one cycle, neither does this one. So these two give us zeros anyway, because any element here in these cycles do not survive into our S4. So the others, you have 5 classes for which you will have surviving elements into S4, and for them we want to find out the compound characters. Now, one of the things that we need is G by H, which of course is 120 by 24, that's a 5. So that's given. Then you have to multiply that by HL by GL. Remember, we are dealing with the identity transformation, so we don't have to worry about any other factor coming from the representation of S4 itself. Those factors are always 1. So here it's pretty easy to fill the whole thing up. This is simply going to be 5 times 1 by 1. That's simply 5. The next one is going to be 5. Let us now move on to this particular class. This consists of 1 2 cycle and 3 1 cycles. Of course, when we look at the corresponding element in S4, we have to freeze one of the 3 1 cycles. So we are left with 1 2 cycle and 2 1 cycles. That is, we are going to land up in this class. Of course, all the elements here are going to land up in this class. So what we have to do is calculate 5, which is of course 120 by 24, the G by H, times HL, which is 6, divided by GL, which is 10. So 5 times 6 by 10, that's a 3. Similarly, this one, after you freeze the single one cycle, will give rise to this particular class in S4. So for this, the compound character will be 5, that's the G by H, divided by 15 times 3, that's going to be 1. What about this one? 3, 1 square. Once we freeze one cycle, you are left with 3, 1. So what you are going to get here is 5 times 8 by 20. That's 2. And finally, this one is the only one left. 4, 1, when you freeze the one cycle, you're going to be left with 4 here. So it's going to be 5 times 30 by 6. 5 times 6 by 30. And that's going to be 1. So this is our first compound character that we get from phi 1, namely shy 1. Is this a compound character or a simple character? That's pretty easy to check. All I have to do is figure out how much this quantity is. 1 over 120. 1 times 5 square plus 10 times 3 square plus 15 times 1 square plus 20 times 2 square plus a 0 here, I'm not bothering to write that down, plus 30 times 1 square. And how much is this? This is 25 plus 90, that's 115 plus a 15, that's 130 plus 80, 210 plus a 30, 240. So this gives me 2. So the first thing that we learn is that this is not a simple character. This would have come out to be 1 if this had been a simple character, but it's not. In fact, from the fact that this is 2, I can figure out that this has exactly 2 simple characters occurring once each. 1 square plus 1 square equals 2. And one which will definitely occur here, that's pretty easy to figure out, is chi1. Note that all these numbers are positive, and when we take the inner product with chi1, which has only positive numbers, I must get a positive number. In this case, that positive number has to be 1. So let's check whether that is really true. If you calculate 1 by 120 times, okay, let me just write things down directly here. 1 times 1 times 1, that's 5. 10 times 1 times 3, that's a 30. 15. 20 times 1 times 2, that's a 40. Nothing from this. 30 times 1 times 1, that's a 30 plus nothing else. So let's just check. This is 20, 90, 50, 90, 120 by 120 equals 1. So chi1 occurs exactly once in shy 1. So how do we find out the corresponding simple character? Because once you take chi1 away, whatever is left has to be a simple character. There being only 2 of them here. Let me just get rid of this calculation which has served this purpose. And now, subtracting the chi1 from this will immediately give me my simple character, the third simple character in my table, 4, 2, 0, 1, minus 1, 0, minus 1. Now, if you really wanted to check to be sure, you can find out the inner product of this one with itself. That's going to be 4 square, 16 plus 10 times 4, that's 40, plus 20, plus 20, plus 24. This whole thing divided, of course, by 120, and it should be easy to check that this is exactly equal to 1. So this is a simple character. Let us now continue with phi 2, the second simple character for our subgroup S4. From this, we should be able to get shy 2, and that should be pretty easy to write down. In fact, the only difference that will happen between this one and my shy 2 is that these two classes are going to contribute minus 1. These two classes, when you get them from the superclasses out here, of course you get to 2 1 square only from 2 1 cube, and you get to 4, which has minus 1, only from 4 1. So for these two, 2 1 cube and 4 1, the character is going to change sign between shy 1 and shy 2. So you are going to get 5 minus 3, 1, 2, 0, minus 1, 0. Now in this case, it's pretty straightforward to check that this does not have chi1 in it. In fact, we should check before that this is really not a simple character by taking the inner product of this character vector with itself. It will turn out that it's not, and it will turn out that it has exactly 2 simple characters in it, and the one which it does have will turn out to be chi2. And frankly, you don't even need to calculate this all over again. You can see that exactly the ones which became minus here are the ones which also has minus signs in chi2 here and here. Remember, all you have done to go from the classes here to the classes here is freeze out one cycle. Freezing out one cycle, or in fact freezing out any odd cycle, will not change the parity of the permutation. So, whatever parity you had here, you have the same parity down here as well. So, two minuses, ultimately when you calculate the inner product, you get exactly the same thing as you had when Chi1 was dotted with Chi1. Here Chi2 dotted with Chi2 will give you the same thing, and that will tell you Chi2 has Chi2 exactly once. So by subtracting out Chi2 from Chi2, I should be able to get one more row in the character table, one more symbol character, which turns out to be simply 4 minus 2 minus 1. Sorry, 1 minus 1, that's 0. 2 minus 1, that's 1 again. 0 from which you subtract minus 1, that gives you plus 1. Minus 1 from which you subtract minus 1, you get a 0. 0, that's a minus 1. So chi3 and chi4, 2 simple characters have been obtained simply from phi1 and phi2. At this stage, things seem to be going exactly the same way as for the previous example, only with a larger number of elements. But things will begin to change soon. Let us now figure out the next compound character in line, that is chi3, for which of course I am going to use phi3, the third row of my character table for S4. Once again, these two particular classes have no elements in S4, so they are going to contribute 0 anyway. And just for convenience, let me quickly write down the values from the character table that you have here, the corresponding phi values, along with the corresponding classes which they come from. 1 to the 5, of course, goes to 1 to the 4 after you feed out 1. So the 2 here goes here. 2 1 cube, that goes into 2 1 square, that gives you a 0. The 2 square one gives you a 2 square, which gives you a 2. The 3 1 square gives you a 3 1, that of course has a minus 1 in my character table. And finally 4 1 gives you 4, which has a 0 in the character table. So these are the phi L tau values which I need to multiply G by H into HL tau by GL tau by, and then sum up over all the inherited classes. Here of course, as we have said before, one class of Sn goes over to exactly one class of Sn minus 1 or none at all. So this sum is really trivial. So all you have to do here is multiply G by H into HL by GL by the corresponding character values. And here we have already done G by H into HL by GL in forming Chi1. So all you need to do is take the Chi1 characters and multiply them by the corresponding values for phi L here, and that will quickly give you the values 10, 0, 2, minus 2, and finally 0. So this is the compound character Chi3. Now, what's so new about this? Well, let me just check. Is this a compound character? The answer is yes, because you can easily see 100 times 1 plus 4 times 15, that's 160, plus 4 times 20, that's another 80, that's 240, which is of course double of 120. So this has exactly 2 simple characters in it. So this definitely is a compound character. Now, does it have chi1 in it? Let's check. 1 times 1 times 10 plus, I'm just going through the non-zero values, plus 2 times 15. So 10 plus 30, 40, minus 40, and zeros everywhere. So there is no chi1 in it. What about chi2? Well, you can easily see that the ones in which chi2 differs from chi1, this particular compound character has zeros. So the inner product between chi1 and chi3 will be exactly the same, namely 0. So chi2 is also not in it. The inner product of chi3 by chi3 is going to be, apart from a factor of 1 over 120, the sum here, 1 times 4 times 10, that's 40. This one contributes nothing. Neither does any one of these others, but this one contributes minus 2 into 1 into 20, that's minus 40. And hence, chi3 dot chi3 is also 0, and therefore, there is no chi3 component in chi3, neither is there a chi4 component. So, chi3 has two simple characters in it, and this is what is new now. Chi3 does not really have any of the previous simple characters that we had worked out in it. So, here, we have no choice but to call this chi5 plus chi6. The chi5 and chi6 are two simple characters which we have not yet found out. So, this is what is new about this example. In all the previous examples, after taking away the simple characters that you had already found from the compound characters, you could figure out what the next simple character was. At this stage, you can't. So let's go on and talk about the next compound characters in the chi4 and chi5. Let's do them together. In fact, for chi4 and chi5, all that is going to change between chi3 and these cases is that these character values are going to be, instead of those from phi3, those from phi4 and phi5 respectively. So let's just briefly write them down here for our convenience. 3, 1, minus 1, 0, minus 1. And for chi5 is 3, minus 1, 0, and plus 1. So, the rule again is simple. You just take the chi1 values, multiply them by these numbers. So, what you are going to get are 15, 3, minus 1 times 1, that's minus 1. 2 times 0, that's of course 0. These are zeros anyway. And minus 1 for this one. And this one is going to be 15, minus 3, minus 1, 0, 0, 1, 0. Yeah. Let me just get rid of these S4 character values from this table so that it begins to look a bit better. It should be easy enough to check that both chi4 and chi5 are actually compound characters. In fact, if you tried chi4.chi4, what you would get is 1 over 120 times 15 square times 1, that's 225, plus 9 times 10, 90, 315, plus 15, that's 330, and 30, 360. So you would get 3. Since this is the sum of the squares of the number of times simple characters occur in this, a value of 3, something different from 1, immediately shows that this has to be a compound character. But it's also easy to figure out that the only way you can have a 3 in this sum is that it has 3 distinct simple characters in it, once each. By the way, you could have figured out that chi4 is a compound character even without going through this, for the simple reason that the dimension of chi4 is way too big. Remember, the squares of the dimensions of the irreps have to add up to the size of the group. Chi4 is 15 dimensional. 15 square is 225, which already exceeds 120, the size of the group. So this has to be a reducible representation. And as we have seen right now, it has 3 irreducible representations built into it. Since the elements of chi5 differ from those of Chi4 at most in a sign, it's easy to see that Chi5's inner product with itself is exactly the same as Chi4 dot Chi4, and hence that also is equal to 3. So both Chi4 and Chi5 contains 3 copies or 3 different irreps exactly once. Let us now ask ourselves the question, which one of the 4 irreps that we have already identified, Chi1, Chi2, Chi3 and Chi4 are in Chi4 and also in Chi5? Now it is very easy to do the calculation. I am not going to bore you with the details, but if you calculate the inner product of Chi1 with Chi4, you will find 0. Chi2 with Chi4 will also come out to be 0. Chi4 dot Chi4 is 0 too. It's only Chi3 dot Chi4 which is 1, which means Chi4 has Chi3 in it exactly once. Very similarly, you can show that Chi5 has Chi4 in it exactly once. Therefore, we can actually get rid of Chi3 and Chi4 from Chi4 and Chi5 respectively just by subtracting out the character vectors, and this gives us a new set of 2 compound characters. Now these are still compound characters. Remember, Chi4 had 3 irreps in it. I've just taken care of 1. Now what can this particular character vector be? This has in it exactly 2 irreps, none of which are among the ones that we had found before. Chi1, Chi2, Chi3 and Chi4, none of them feature into this. So it has to be a sum of 2 of the irreps which are not among Chi1, Chi2, Chi3 and Chi4. However, note that Sn has only 7 irreps. Chi3 is already a sum of 2 of the unknowns, Chi5 and Chi6. So this one cannot be a sum of 2 more irreps. There simply are not that many irreps going around. So one of the 2 irreps which occur in Chi3 must also occur in this Chi4 minus Chi3. Calling that particular irrep which occurs in both this and this Chi5, we can write this as Chi5 plus Chi7. Of course, a very similar argument can be made about Chi5 minus Chi4, which also contains 2 irreps, and it can be written down as Chi6 plus Chi7, where Chi6 is the yet unseen or yet to be seen irrep. So how do we find out the individual character vectors for the irreps from this? Simple, if you just add these 3 and have the result, you are going to get Chi5 plus Chi6 plus Chi7, which is simply seen to be this. 10 plus 11 plus 11, that's 32 divided by 2, that's 16 goes here, and so on. And so you can find out Chi5, for example, from this simply by subtracting Chi6 plus Chi7, which is here, from this line, and this gives you Chi5. A 5-dimensional irrep with these characters. Chi6 and Chi7 can also be found out simply by subtracting Chi5 plus Chi7 and Chi5 plus Chi6 respectively from this sum, and that gives you Chi6 and Chi7. So what we have managed to do is, starting from the character table of S4, we have figured out the entire character table of S5. After clearing out all the intermediate lines of calculation, this is what my final character table for S5 looks like. If you remember the relative ease with which we worked out the character tables of S3 and S4 respectively in the last lecture, and compare that with the amount of effort we had to give to figure out the S5 lecture here, and definitely if you carry out our homework, which is figuring out S6's character table from that of S5, you would realize that the amount of effort needed is becoming bigger and bigger as you go higher and higher in N. And one thing that actually complicates matters here is that in each of these cases, we are actually going from Sn minus 1 to Sn. In other words, we are using only one subgroup of Sn, the one in which one element is fixed and the other n minus 1 elements get permuted among each other. Now, what we will do is take a look at an alternative approach, again due to Frobenius, and this time we are going to use a simpler version of Frobenius' theorem, the one which corresponds to the identity irrep of H. But what we will do is that instead of looking at one subgroup of G, we are going to look at several subgroups. For each of these subgroups, we will just use the identity irrep and identity irrep alone, but that will be sufficient for us to figure out enough number of compound characters. Let me first remind you of what a partition is. A partition lambda, written within a bracket to indicate that it's a partition, of n essentially is a tuple of n non-negative integers, lambda 1, lambda 2 up to lambda n, which are strictly non-increasing. That is, lambda 1 is definitely bigger than or equal to lambda 2, which is bigger than or equal to lambda 3, all the way down to lambda n, which is bigger than or equal to 0. Where lambda 1 through lambda n, these numbers add up to n. So a partition basically is a way of breaking up the number n into integer pieces. Now, for each partition of n, what we can do is form this direct product group S lambda 1 times S lambda 2 times S lambda 3 times S lambda 4 up all the way up to S lambda n, and this is isomorphic to a subgroup of Sn. Basically what we are saying here is, in Sn we have permutations, all possible permutations of n objects. But if we only confine ourselves to situations where the first lambda 1 of these objects permute among themselves, the next lambda 2 among themselves again, the next lambda 3 again among themselves, and so on, then we actually get this particular subgroup of Sn that we are talking about, which essentially is the direct product of S lambda 1, S lambda 2, S lambda 3 all the way up to S lambda n. This is a subgroup, of course, of our original group G, which is Sn here, and it's obvious that every partition of the integer n will yield one such subgroup, and using the simple version of the Frobenius formula, psi L is G by H into HL by GL, for each one of these subgroups gives us a set of compound characters. Now, how many such compound characters can we get in this manner? We will of course get one compound character for each such subgroup, and that means that I will get one compound character for each partition of the integer n. We do know that there is a one-to-one correspondence between partitions of the integer n and cycle structures of the permutation group, and hence between partitions on one hand and classes of the group Sn on the other. So we get exactly as many compound characters as there are classes. Remember, NC, the number of classes, happens to be exactly equal to the number of simple characters that any group has. It will turn out that these characters, the compound characters we get, are all linearly independent, and they are of course linear combinations of the MC simple characters, and we can actually work out each one of the simple characters just from these compound characters directly. The proof of this is a bit involved, and we are going to cover the proof in the next lecture. However, in this one we are going to actually use it to figure out the character table for S6, and then while working it out you will see that you can actually figure out all the simple characters of S6 from the compound characters that you work out this way. Why S6, you ask? That's simply because we have already worked out all the character tables up to S5 using the previous method. So, with this new method, we are going to try the next one. But before we jump into the full calculation, let us take a look at a particular example. Remember, we are going to work this for one for each partition. So right now let's consider a particular specific partition of 6, which is just 3 plus 2 plus 1 makes up 6. Now, this will of course give us S3 direct product with S2, direct product with S1 as the subgroup of S6 that we are looking at. Of course, this means that out of the 6 objects which are being permuted in S6, we are only going to consider those permutations in which the first 3 of these objects permute among themselves, the next 2 permute among themselves, and the last one does not move at all. So this is the subgroup that we are looking at, and now using our description here, we will try to figure out the compound characters corresponding to each and every one of the classes. Let us now take the classes one by one. But before that, the numbers which are common for all the classes. G, the order of the group S6 is of course 6 factorial, that's 720. H, the order of this subgroup is simply 3 factorial from S3 times 2 factorial from this times 1 factorial from S1, and that gives us a total of 12. So the G by H ratio, which is there in every one of these calculations, is actually 60. Of course, what we need to do next is go through the classes of S6 one by one and figure out the ratio HL by GL for each one of them. Let me remind you once again, GL here is the number of elements in the nth class, and HL is simply those elements in the nth class which survive into our subgroup, namely in this case S3 cross S2 cross S1. The class we will consider here is the simplest of all the classes. The class which has cycle structure 1 to the 6, which means 6 1 cycles. Of course, this means that the only element in this particular class is the identity. None of the elements move, and of course this element definitely survives onto the subgroup H. So here we have very simply GL equals 1 and HL equals 1. So our compound character value for this particular class, G by H into HL by GL, is simply 60, the same as G by H. Now let me point out something about the notation here. Of course, we had been using a notation earlier which had L, the class index sitting here. Here I have just written down the actual cycle structure which tells you which class we are talking about. Now there has been a slight change in the notation as far as the superfix goes. In the earlier case, we were actually taking a look at each irrep of the subgroup H, and from each one of the irreps you were getting a compound character. As a result, what we were doing was labeling the particular compound character we are talking about by using the label for the irreducible representation of the subgroup. In this case, however, we are only using one irrep of the subgroup. It is a subgroup which changes according to which partition we take. So here, what we have done is we have indicated which particular compound character we are talking about by using the partition itself up here. So our notation will always have psi with the partition as superfix and the class identity as a suffix here. So all the characters that we are going to calculate in this go are going to have psi with a 3 to 1 superfix. Of course, the class label is going to change from class to class. And in this particular case, you have this simple value of 60. So let us now move on to the next class, which has smaller number of 1 cycles because a 2 cycle has come in. This, of course, is a class which has elements with 1 2 cycle and 4 1 cycles. Of course, the number of elements here in this class can be easily figured out using the formula that we had worked out earlier. GL is simply n factorial, in this case 6 factorial, divided by 2. That's because each 2 cycle can be written in 2 different ways, divided by 1 to the 4, which of course is just 1. Each 1 cycle can only be written down in one way, but the 4 1 cycles can be permuted among each other without changing the particular entity that we are talking about. So the number of distinct permutations which make up this particular class is 6 factorial divided by 2 divided by 4 factorial, which turns out to be 15. So we know our GL. The question is, how many of these perturbations survive into the subgroup S3 cross S2 cross S1? Of course, every permutation I am talking about here must have 1 2 cycle and 4 1 cycles. Now let us focus on this 2 cycle. Where can this 2 cycle come from as an element of this subgroup? Now, you cannot have a 2 cycle within S1. So the 2 cycle must have come from either S3 or S2. Now, if it is going to come from S3, that is, you have 1 2 cycle and 1 1 cycle in S3, and the other 3 1 cycles are coming from S2 and S1 respectively, then from S3 we have a choice of 3 possible permutations. If you don't see right now how that comes about, one way to think about that is simply because out of 3 objects, we are forming a 2 cycle, which means 2 of them have to be chosen, 1 stays outside, and that one which stays outside can be chosen in 3 ways. That's a rough and ready way of calculating the thing. The other way would simply be to look at the fact that we are looking at S3 and the number of permutations in that which has exactly 1 2 cycle and 1 1 cycle, which is of course what we need here from S3, must be this. So that's of course 3. Once you have chosen the 2 cycle and a single 1 cycle from S3, you have to of course choose 2 1 cycles from S2 and the last 1 cycle from S1. Here there are no choices left because there is only one way you can get a permutation with 2 1 cycles, namely the identity out of S2, and of course there's only one element in S1 anyway. So if the 2 cycle comes from S3, there are exactly 3 ways of doing it. All the 3 choices are basically because S3 allows you to have 3 different permutations with 1 2 cycle and 1 1 cycle. But that's not all. You can also of course take the 2 cycle out of S2. Now if you take the 2 cycle out of S2, that can be done in only one way. S2 after all has just 2 elements. One of them has 2 1 cycles, the identity. The other one is the single 2 cycle. 1 goes to 2, 2 goes to 1. And of course, once you have chosen the 2 cycle to be something which is in S2, then S3 must give you 3 1 cycles, which is the identity element, only one possibility. And S1 of course must give you one element anyway. So if the 2 cycle came from S2, you actually have only one way of doing this. So overall there are 4 different permutations which will have 1 2 cycle and 4 1 cycles and will survive into our subgroup S3 cross S2 cross S1. And that means our HL here is 4. And because HL is 4 and GL is 15, our character value for psi upper 3 to 1, remember once again that's the partition, and suffix 2 1 to the 6, which is the class label. Sorry, this is 2 1 to the 4. Must be 60 divided by 15 into 4, namely 16. Our next class has a larger number of 2 cycles and compensates by having a smaller number of 1 cycles. So this is the class labeled by 2 square, 1 square. 2 2 cycles, 2 1 cycles. And using our standard formula, the number of elements in this class is given by 45. Now let us figure out exactly how you could get a permutation with 2 2 cycles and 2 1 cycles into our subgroup S3 cross S2 cross S1. Now one of these 2 cycles must come from S2 and the other one must come from S3. Here there are no other choices. Of course this means S2 must have the 2 cycle alone and S3 must have 1 2 cycle, 1 1 cycle. We have already seen that in the case of S2 there is precisely 1 permutation with 1 2 cycle, whereas in S3 there are exactly 3 permutations with 1 2 cycle and 1 1 cycle. So here the only possible number of permutations which go into S3 cross S2 cross S1 from this particular class happens to be these 3. 3 times 1, that is. So HL is 3, and therefore our compound character for this one is simply 4. Our next class has 3 2 cycles. This has a GL which you can easily calculate using 6 factorial, that is n factorial divided by 2 cube into 3 factorial, which works out to be 15, but this calculation is a bit of a waste, because if you see that here we are demanding our permutations each to have 3 2 cycles. Now, in the subgroup that we are considering right now, we have an S3 and S2 and an S1. And S1 simply cannot have a 2 cycle. And there is no way you can fit 3 2 cycles into this subgroup. Therefore, HL is simply 0, and our corresponding compound character is just 0. The next one, 1 3 cycle, 3 1 cycles, is a class with 40 elements. Now, the 3 cycle that we are going to look at must come from S3. There is no option. And then the S2 must have 2 1 cycles and S1 must have 1 1 cycle. No choices there. The only choice is in which permutation of S3 has this 3 cycle structure. There are actually 2 permutations of S3 which has this 3 cycle structure, easily figured out by the formula 3 factorial by 3, which is 2, or you could just simply figure out that this has to be the cyclic permutation 1, 2, 3, or the anticyclic permutation 2, 1, 3, these 2 cycles. Anyway, ultimately this tells us that HL has to be 2. So our formula is simply 60 divided by 40 into 2, and that gives us a value of 3. Now I can keep on going for each and every one of these classes, and there are exactly 11 of them as far as S6 is concerned, but frankly there's nothing much more to be learned from repeated calculations. Okay, maybe one more. 3 2 1. This is the class with 1 3 cycle, 1 2 cycle, 1 1 cycle. Of course, in this case, the 3 cycle must come from S3, the 2 cycle must come from S2, and the 1 cycle must come from S1. But a 3 cycle can come from S3 in 2 ways, whereas the 2 cycle can come in only one way from S2, and you can have only 1 1 cycle in S1, because that is all you have. And HL therefore is 2. GL, as you can easily figure out, is 120, and this gives us a compound character value of 1. So going through all of these cycles in order is pretty straightforward. In fact, the next few are very, very simple, because if you are looking at 3 square, you need 2 3 cycles. You can't have 2 3 cycles in our subgroup because you don't have enough space there. Remember, in our subspace, the first 3 elements were moved among themselves. There you can accommodate 1 3 cycle. The other 2 factors which built up this thing are S2 and S1. They don't have the place for a second 3 cycle. Similarly, 4 1 squared, a single 4th cycle cannot be accommodated in any one of these pieces. Our S3 cross S2 cross S1 cannot have any element which survives into that. Same for 4 2, same for 5 1, same for 6. So all of these correspond to characters of 0. So in a way, once our cycles become too big, they can't fit into our pieces of Sn that we have broken up Sn into. So if you try to form the full compound character table in this manner, you will find there will be typically a lot of zeros near the end. Anyway, if you put all of them together, in the order in which we have classes with increasing sizes, the way we have ordered them in this calculation, then we are going to get the following values for the character components. They are going to be 60, 16, 4, 0, 3, 1 and then 5 zeros. Notice that I have written down the sizes of the corresponding classes on the top in blue here, and this will be very handy in checking whether this is a compound character or a simple character. Actually, we already know that this has to be a compound character. The identity here has a value 60. This is a 60-dimensional representation that we are really talking about. And you cannot have a 60-dimensional irreducible representation for S6 which has only 120 elements. Remember, sum of the squares of the dimensions have to add up to the number of elements. 60 square is already way too big. But anyway, given this, let us try to figure out shy.shy, and for that we will need the occupancy of each classes. A simple straightforward calculation will give you 12. This not being 1 immediately tells us that this actually has to be a compound character and not a simple one. The corresponding representation, as we have been saying, is definitely reducible. However, at this point this may look like a bit of a problem. 12 irreps occurring once each is not a possibility because we know that S6 has 11 classes and hence only 11 irreps. But this does not rule out the possibility that you have one irrep occurring twice, that takes away 4, and then you have 8 other irreps occurring once each, or many other possible combinations. Now, since figuring out the simple characters from these compound characters requires to know exactly how many of the previously obtained simple characters are already in this compound character, this may seem like a bit of a drawback. But that's basically because we have started somewhere in the middle. If we had gone through the partitions one by one in sequence and formed the entire compound character table, the whole thing can be made a lot more systematic, as I will quickly illustrate in the time that is left for this lecture. Here is the complete compound character table calculated using this method for S6. We have calculated the compound characters corresponding to each partition, and the partitions we have put in a opposite order to the one which we have used to label these classes. So, shy upper 6 goes first. Now, upper index 6 here means that we are considering a partition where you have all the 6 objects in one place. This, of course, is nothing but the group S6 itself. So, here the subgroup H is the same as the group S6, and this very trivially gives me the identity representation, which obviously is already irreducible. Being one-dimensional, it cannot be rendered any smaller anyway. Now, let's look at the next one, shy 5 1. Something we have not calculated here. In fact, we have only calculated this one so far. There are 10 more to calculate, or 9 more if you think that this is trivial and you don't need a calculation for that. So it's really a bit lengthy, but as you can see, by looking at the entire character table, once you go to these classes where you're talking about breaking up more and more of the number 6 into smaller pieces, which means you're going to end up with only small cycles accommodated, you're going to get a lot of zeros. So all of these have lots of zeros simply because you cannot have any of the permutations in the original group, which could have large cycles, fit into this. So here, for example, this corresponds to the subgroup S2 plus S2 plus S2. So if you have anything larger than a 2 cycle in your original permutation, that will not survive into a subgroup. And that gives you all these zeros. So although the calculation may look pretty lengthy, it's really not as lengthy as it looks, because many of the results can be just trivially written down to be 0. However, this is still quite a lot of calculation, and there are ways of doing this even more efficiently. And those are things we are going to explore in the next lecture and even further in the next one. But for the time being, let's focus on this particular compound character. Let me just make some space so that I can do some calculations here. The fact that this is compound is easily seen because if you dot this particular character vector with itself, you get 1 by 720 into 36 into 1 plus 15 into 16 plus 45 into 4 plus 40 into 9 plus 120 into 1, of course, plus 90 into 4 plus 144. And a quick calculation will show you that this has a value of 2. And this really means that this has 2 simple characters in it, and it's rather obvious that this one has to be in it exactly once. And this means that if you get rid of this and in its place write down the difference between this compound character and this one, which we already know is a simple character, then we are going to get a simple character. That is 5, 3, 1, minus 1, 2. Remember, we are subtracting the upper row from this one. You get 0 here, minus 1 here, 1 here, minus 1 here, 0 here, minus 1. So this is our second simple character after this first one that we have figured out. After cleaning up the table and labeling these characters, which we already know to be simple characters, by chi instead of the chi that we have been using so far, we now need to focus on chi 4, 2, which happens to be this particular bunch of numbers: 15, 7, 3, 3, 3, 1, 0, 1, 1, 0 and 0. Of course, we need to check that this is really compound. That is, we need to dot this character vector with itself. Then we need to dot it with the previous one to see how many times, if at all, they occur here. And then get rid of those occurrences to try to get a simple character. But the calculation here tends to get a bit too long. And, well, calculating something like 1 times 15 square plus 15 times 7 square, etc., etc., etc. is not really that straightforward to do, especially while I am recording this directly. So what I will do is I will make use of a simple computer algorithm. I should not really even call it an algorithm. I'm just going to do this calculation using the NumPy module from Python. So for those of you who already know NumPy, this should be pretty easy to understand. Even if you don't know NumPy, it should be pretty easy to follow what we are doing here. So I've already put in some important things which we will need. Of course, I've imported NumPy as NP. This is the standard mantra that everybody uses in a NumPy program. And then we have declared a few NumPy arrays. The first one is an array which I am calling n's. And these are nothing but the number of elements in each of these classes. So that's what goes here. I have created a list with these numbers first, 1, 15, 45, etc. That thing within the square brackets is a Python list. And I have converted that into a NumPy array using this numpy.array function. Then we have created another array, which I'm calling P1. And from the name in itself, ones, it should be obvious that this one has 11 ones in it, which of course is this particular simple character. So P1 is just our first simple character array. P2 is nothing but this one. I've just written this down here. And our compound character 15, 7, 3, 3, etc., etc., that's the one which has been stored in this side. And G, this number, is of course 720, the order of the group. Let's first check whether psi is actually a compound character or not. So let's figure this out by simply multiplying psi by itself. In an array, multiplication is element by element, so that's pretty straightforward. You have to also multiply that by the elements of n's and then divide by g after summation. So what we are really going to do is to calculate this. Sum of n times chi, or chi square would also work. Both of them work equally well, divided by g. And this should tell us whether this particular compound character is actually a compound character or a simple character. The number works out to be 3. This of course tells us that this has 3 irreducible representations occurring inside. Now which ones? Is P1 in it? That's easy to figure out. All you have to do is calculate this sum. Instead of multiplying psi by itself, you have to multiply psi by P1. Element by element, also element by element with ends, divide by G, and you get exactly 1. So, chi1, our first irrep, occurs exactly once. What about chi2? It also occurs exactly once. Which of course means that our new simple character would simply be the compound character minus P1 minus P2. And so this gives us our compound character as this. This gives us our simple character as this. So this is our third simple character that we have found out, a 9-dimensional representation with the character values 9, 3, 1, 3, 0, 0, 0, minus 1, 1, minus 1, 0. Of course, we should check whether this is simple, although from the foregoing it should be sort of obvious. But let's still do it because it's pretty easy to do it using our program. All you have to do is dot P3 with itself, and that gives us 1. So P3 is a simple character, a character of an irreducible representation. Now we can go through this step by step until we get 11 simple characters. And I guarantee you that if you follow this stepwise, at each stage you will be able to figure out the next simple character. So this is a perfectly algorithmic process for calculating the final answer. That is the character table for S6. There is no denying that this particular approach that we have used now is definitely easier to use than the earlier one, especially because we are using the Frobenius theorem in its simplest version here. However, getting all the HL values correct may prove to be tougher than it appears at first glance, especially because there may be a situation where the same cycle structure in your original class can be replicated by taking such classes from different pieces of the subgroups in multiple different ways, and you have to make sure that you have considered all of possible ways. We will see in the next lecture that there is a very neat way of representing this calculation using symmetric polynomials. This will actually make determination of these compound characters somewhat simpler. The added advantage is that it will also allow us to prove the assertion that I had made, that this approach definitely leads to independent compound characters so that they have sufficient information to give us all the simple characters. This is what we are going to cover in the next class. That is not going to be the end of the path, however, because we will see later that using a rather nice algebraical trick, we can actually modify this approach so that it directly gives us the character table. That is, the simple characters, and it is this approach which ultimately will lead in its graphical version to the theory of Young tableaus. But that is all going to come in a later part of this lecture series. Bye for today.